All right, let's get started. So today we're going to continue our series of lectures on network security. And the topic of today's lecture is going to be focused on messaging systems. So security in the sort of a text messaging environment. And this turns out to be a pretty interesting and hard problem. There are several reasons why it's worth looking at these. There's a lot of interesting techniques here that end up being applicable in the context of building networked systems where you have to operate over the internet or some other untrusted network. And it's a pretty active area of both research and deployment of real systems. And it's still not a solved problem. So the Zoom system we're using right now does some questionable things. Now, it's only been fairly recently that researchers have started finding some of the weaknesses and potential problems in Zoom, but you can see that even widely used systems still have some maybe questionable designs and could be improved further. So in this lecture, I'm not going to talk much more about Zoom. I think it's not super well known yet what the internal details are. We'll see how this shakes out. But there's a lot of sort of good ideas in this paper nonetheless about other techniques and systems that we can look at and hopefully learn from. So please interrupt if you have questions or comments anytime. Hopefully this will be interactive like we've tried to keep up in the past. So the content, the sort of goal for all this message security business is that we have two users. Let's say we have Alice and Bob over here. And Alice wants to send some kind of message over to Bob. And there's different properties you might care about in this context. Probably the first one that comes to mind is some kind of a confidentiality goal. So we would like to make sure that the messages that Alice is sending to Bob cannot be read by anyone other than Bob or by Alice since she sent the message. Another property you might worry about is authenticity. So are we sure, or to be more precise, is Bob sure that the message he gets over the network actually came from Alice? Or could this be a fake message from someone else? Did Alice just send this now or not? And the paper actually has a litany of other properties you might worry about. So this is maybe one way in which messaging security differs a bit from the secure channels we've looked at last week, is that there's a lot of sometimes conflicting goals for a messaging security application and harder requirements than what we've seen for just secure channels in the past. And the contexts are a little bit different. So messaging is widely used in practice. There's email. Why isn't email secure? That's one, I think, obvious question here. So email is widely used and has been around for a while, but unfortunately, it doesn't really provide super strong security properties. So one thing going on with email, we'll sort of look through several things that make securing email difficult. One thing going on in email is that it's a very complicated system in terms of how your message travels from Alice to Bob. And there's many trusted entities along that path that make it difficult to have a strong assurance of security. So imagine that in our setting, it's actually Alice wants to send an email that eventually makes its way to Bob. How might this look like? Well, first off, probably Alice is using her computer to type in the email message. The computer, in turn, is going to interact with some server over the network. Maybe Alice is using Gmail. So that's another trusted entity. We need to worry about the computer correctly sending your message to Gmail while that stays confidential. Gmail itself, once you hit send, is going to transmit your email to the destination email server for the recipient named in your message. So maybe the recipient that Alice sends to is a group of friends that includes Bob. So maybe there's some kind of a mailing list server. And this mailing list will send the message to probably many of Alice's friends, including Bob. So maybe Bob has an email address, bob@ibm.com. And this email address causes the mailing list server to look up how to send email to ibm.com and send the email message to Bob at that address. Now, Bob might not actually use ibm.com mail servers to read his email message. He might be forwarding the emails, like probably many of you guys forward your MIT email to Gmail. That could happen here too. Maybe Bob forwards his email to bob@mit.edu. So as you're seeing, the email is traveling through a lot of hops here on its way to the final destination. And even there, maybe Bob actually doesn't treat his email at MIT's mail servers. Maybe he used as the CSAIL servers, our research lab servers. And there, it's not like the mail goes directly to Bob. There's probably a spam filter of some kind that's going to look at the email message, decide if it looks similar to lots of other email messages that have been received in the past. And if so, if this passes the check, finally it'll make its way to Bob's computer when Bob picks up his mail messages eventually. And now Bob gets to look at that email. And in the email world, this whole sort of path historically hasn't been protected by any cryptography for many of the same reasons that we looked at in the TCP security paper 2 weeks ago. But, and sort of progress has been made to some extent, but it's been slow. So incrementally, people have been trying to add some cryptographic protections to various parts of this whole diagram, but it's been quite slow going. So one reason, sort of what's going on in email security, why it hasn't been super effective, is that many of the security features that we see being deployed for email are retrofits. So it's not like someone sits down and says, oh, tomorrow we're going to run a new email protocol. That seems, you could do this. Any one of you guys could say, well, here's a new email protocol, but the rest of the world isn't going to follow along. There's been some messaging systems proposed that have tried to shift email to somewhere else, but by and large, email has stuck around. And what people have been able to deploy are incremental changes that really work at a hop-by-hop level. So, for example, there's a protocol called Start TLS that worries about the connection between mail servers. So the mailing list server and IBM, or IBM to MIT, or Gmail to this mailing list server. These links could be encrypted at the network level, at the sort of TCP connection level, with the Start TLS extension. That's one of the recent additions to email security. But the problem is that because these are retrofits, they have to be backwards compatible. So as a result, much of these security measures are really opportunistic. So if Start TLS seems to be available, Gmail will use it to talk to the mailing list server and so on. But if it seems to be not available, Gmail and all these other servers will fall back to unencrypted SMTP connections to transfer email messages over the network, which means that an active attacker can force you to downgrade to plain text. Very much like in the HTTPS lecture, we saw downgrade attacks from HTTPS down to HTTP. The same thing happens in this context as well because of this retrofit of opportunistic encryption. Another point to make is that much of the focus in email security has actually been not so much on the properties that we've stated so far, not so much on confidentiality and authenticity, but much more on spam. Because spam is a much more visible and prevalent problem that gets users riled up. So quite a bit of the technology, even cryptographic signing schemes, really have spam control in mind. So if you're curious, you can look up a couple of these things called DKIM, which is a protocol by which Gmail could sign the messages that you are sending through Gmail. And the main use of this DKIM technology is not so much to prove to Bob that your message wasn't tampered with, but more to prove to the spam filter on Bob's mail server that this message really came from a Gmail user and was not spoofed by someone else. So the spam filter doesn't drop these Gmail messages into the spam folder for Bob and instead delivers them as real email. So it's quite a bit focused on spam control, and there's other protocols, DMARC, that specifies whether you should expect a signature or not in the first place. But again, it's opportunistic. It actually falls back to DNS to decide whether that. There's another protocol, ARC, for signing forwarded email messages that IBM could use to sign that it relayed a message from the mailing list to Bob. But you can see that many of these technologies aren't sort of trying to directly address our big goals that Alice and Bob might have had in mind. And the reason why it's hard to do better, I sort of touched on it a little bit, but it's really this compatibility combined with a very diverse base of applications. So there's all kinds of stuff going on in email. There's, of course, Alice talking to Bob. but there's also mailing lists. There's also automated email systems that send notifications. There's archives. There's spam filters. You can do business over email. You can send email to some automated system. All these things sort of expect to speak the same email protocol, which makes it hard to move on in anything other than an incremental fashion. The other sort of big constraint that we'll also see in a little bit in the messaging sense is that email is a very weak building block for security. So there's no centralized registry or directory of users that you could use to do something stronger, like look up a public key. So when Alice sends an email to an email address, she doesn't even know where it's going to end up or which user it is or whether it's a valid email address in the first place. And the whole interaction is really asynchronous. Maybe that's the right way to put it. There's no direct connection from Alice to Bob's recipient's computer or mail server. Alice sort of tosses this email message out, and it makes its way through the system. At no point can Alice really query and say, well, like, let me talk to Bob's server and really figure out what's going on. So it's very asynchronous one-way messaging protocol. That's sort of why I think security has been hard to achieve for email, but also sort of partly why email has been successful is that it's this very malleable and flexible system. And these technologies, maybe to make maybe a clearer point, these technologies that have been opportunistically retrofitted into email don't really give you the end-to-end guarantees that we want. So looking at this picture that we've sort of drawn out here, if you even apply these link-level encryption between Gmail and this mail server and so on, that's still a large number of entities in the middle that have to be trusted. You have to make sure that this mailing list server didn't save a copy of your email message and didn't tamper with it. This server, this server, this server, the spam filter didn't accidentally save it to a world-readable file and so on. And all that's because the email actually turns to plain text at every one of these hops. The encryption is only for the duration of the arrow drawn on this board and not and every time it reaches a new box here, the email message gets decrypted again. So in this hop-by-hop security plan, it's really hard to achieve strong guarantees like what we were hoping for at the top of this board. All right, so that's a bit of a background on email security and where we're coming from. I wanted to ask if there's any questions about this before we move on to more end-to-end encryption schemes.
I have a question.
Yeah, go ahead.
Why do they have to be plain text at each point?
Yeah, okay, so maybe what I should say is that there's nothing that requires your email message to contain the plain text content that you want to communicate. So you could totally send an email message that contains an encrypted version of what you want to send. But it's hard to retrofit this uniformly throughout this protocol stack. So there are systems like PGP and SMIME that I think this paper mentions some in passing at least, where you could layer encryption on top of this whole scheme. So when Alice wants to send a message, she takes the message, encrypts it, and sticks the encrypted stuff into the actual body of the message that she is sending along. It's doable. People do this. People use PGP sometimes. People use SMIME, which is another standard for this sometimes. The challenges really are getting this adopted widely and making this usable and secure. So for wide adoption, I think what's going on is that many of these encryption technologies don't work super well with a bunch of boxes here. Like forwarding messages through a mailing list doesn't really work super well with encryption. Spam filtering doesn't work super well with encryption. Gmail itself doesn't work super well with encryption right now. Or like you have to type stuff in your web browser. That's going to be plain text. Another problem is key management. So we'll spend quite a bit in this lecture talking about key management. But the fact that there's no directory of users in the email universe and that email delivery is asynchronous means that when Alice is trying to send an email message to Bob, she can't look up Bob's public key in any kind of a sensible directory. And she can't ask Bob even, hey, give me your key. She has to toss something into the void and then hope that it works out okay. So having a system designed around some kind of a directory, or at least the ability to look up, hey, give me Bob's current IP address, or give me Bob's, a server responsible for Bob, and I could talk to it interactively when I'm sending. All these would make this a little bit easier to use. So you're strictly speaking right that you could jump through hoops as a user and really do encryption on top of email, but it's hard to make usable and broadly applicable. Maybe that's the answer here.
Thanks.
Yeah. Other questions? All right, so let me move on to what this paper is sort of arguing for as an alternative to email security that's much more hop by hop, is a focus on end-to-end security, where the ends, informally speaking, are going to be the two users, or at least the two user computers in the diagram that we've been looking at here. So this notion of end-to-end message security is going to allow us to hopefully achieve stronger guarantees by having basically Alice's computer encrypt the email, the message being sent. And then even if the message is traveling through many servers along the way, the message stays encrypted. So it's okay if the servers are not fully trustworthy, very much like this PGP strawman that we were discussing before I erased this board. So to get a sense of what this might look like, let's look at a Strawman design that's kind of like PGP, but not nearly as sophisticated. So here's a scheme, like in the previous diagram. We want to have Alice and Bob here, and Alice wants to send a message to Bob. So one thing we could do is, well, how about we just encrypt it? So you might imagine Alice sending a ciphertext C, which is an encryption of the message using Bob's public key. So here's the message that Alice wants to send, and here's the public key of Bob. And she's going to send this ciphertext C, and to make sure that to convince Bob, so this encryption is hopefully going to get us this confidentiality property we were thinking about before. And we're going to need something else, some kind of a signature that's going to convince Bob that this message really came from Alice. So let me sketch out this strawman. So she'll use her secret key to sign the encrypted message she is sending. And just to remind you guys, what I'm sort of inferring is that each user has their own secret key that they're not sharing with anyone else. All right, so in this PGP-like scheme, when Bob gets this message consisting of a ciphertext and a signature, the first thing Bob is going to do is probably verify that this really came from Alice. So Bob will call verify with the public key of Alice, and it'll pass in the thing he wants to verify in the signature, the ciphertext C, and the signature S that he got over the network. And if that checks out, Bob can actually decrypt using his secret key the ciphertext C and get out the message M that perhaps came from Alice. Hopefully that makes sense. Fairly simple looking protocol that tries to achieve both confidentiality and authenticity. So do we actually get confidentiality? So that's, I guess, one thing you might worry about. Do we have a confidential protocol now? Well, I think you might imagine maybe that's true. So what we want to make sure, by confidentiality, what we mean is that we have this message over here inside of the encryption of the ciphertext being transmitted. We want to make sure that only Bob can get this thing out. That seems to be pretty straightforwardly true if we have public key encryption that works. So only Bob, who is in possession of the secret key of B, should be able to decrypt the ciphertext to get the message out. And assuming Alice didn't do anything else silly with the message, like post it publicly, then we're pretty good. Only Bob should be able to get the message out, do this step. That seems probably pretty good. How about authenticity? Can Bob really conclude that this message came from Alice, that the message M came from Alice. So this turns out to be a little bit more subtle. So anyone see a potential problem here?
Well, Alice doesn't necessarily know what she's signing because it's encrypted before she's signing it.
Yeah, so you're exactly right. We didn't actually sign the message. So when Bob verifies, what Bob verifies is that Alice signed the ciphertext. So a potential attack might be that Alice saw some message being sent to Bob. So there's another user over here, some user U. Who knows who this guy is, but he sent another message to Bob, encrypted with PKB, some other message M prime. Alice can't decrypt this thing. But what she can do is send it to Bob as if she sent it and sign it, because the signature just requires signing the ciphertext. So this ciphertext C prime over here, in our sort of hypothetical other user, this is something that Alice could sign. And then Bob will decrypt this message. Bob will get M prime. And with our broken protocol, Bob might now think, oh, well, Alice told me M prime. So turns out we didn't really get authenticity right. So even in the simple strawman, easy to make mistakes. Well, I guess there are several fixes you could imagine here. One thing you could imagine doing is that instead of signing the ciphertext, maybe we should have signed the underlying message. So maybe this should have been the message M, and then when we verified, we should have actually verified the message M. That's pretty good from the perspective of really signing what you mean. So now we're really signing the message being sent, and this is no longer susceptible to Alice impersonating a different user's message as her own. Another general scheme for what you might do is perhaps add more explicit identifiers into the message being sent. So instead of just sending the message M, maybe there should be a thing in the message saying, this is a message from A to B. That makes sense, hopefully. Any questions? All right. I think someone's Skype is ringing there, maybe, but we'll see.
One question.
Yeah.
How would you get the other person's public key?
Like, yeah. Oh, yeah. So that's like a whole. Yeah, that's going to be a huge chunk of. I think this lecture is going to be looking at how do you get users' public keys. So in this particular context, we're assuming that the users somehow already have each other's public keys. That's roughly the assumption that PGP makes. But actually getting the public keys around is as very much like we saw in the certificate lecture last week. It's like where quite a bit of the action is. How do you exchange keys to begin with? Make sense?
Yeah, thank you.
All right, super, yeah. All right, so sorry, there's a Skype sound. Let me double check if there's a.
Might be your iPad.
Yeah, perhaps. Huh. Yeah, I don't think it is, but all right. Well, we can hope that it times out eventually. Yeah. Slightly distracting. All right. Sorry about that. So let's start out here. Let's get back to sort of discussing the various properties. So our protocol didn't really have authenticity in the sort of original strawman that I proposed, but we do have authenticity by either signing the right message or signing the intended, or sort of having the encrypted message contain the intended sender and recipient. One thing I want to point out is that even though the underlying protocol might have had confidentiality, the system built on top of it might not have had confidentiality because we didn't have authenticity. What I mean by this is that it might have been the case that we didn't have authenticity, so this message M prime could have been interpreted by Bob as if it was coming from Alice. And that in turn might have compromised confidentiality. So Bob might have seen this message and responded back to Alice saying, hey, Alice, did you really mean M prime? What are you talking about? And all of a sudden, Alice gets a copy of M prime. So I think it's important to realize that in these protocols, if you have one weakness, it might turn into a problem in some other dimension that you weren't expecting. So the last point I want to make is that there's sort of other potential properties that you might worry about other than just confidentiality and authenticity. And in particular, replay attacks are a common problem that you might run into. So here, you might ask yourself, like, what happens if the adversary is watching the network and takes this message that he sees, C and S, and saves it, and sends it again tomorrow? So at least in the simple scheme that we've described so far, Bob will look at these messages again tomorrow and again think, oh, that's great. Alice sent the same message again. And that might be problematic. Maybe in a sort of a text messaging application where Alice and Bob are just chatting, maybe that's not a big deal. Bob will just respond back and say, like, oh, you just said this yesterday. What are you talking about? But in some more serious context, if this message says, you know, please go and buy this thing, and I send it again and again, if Bob isn't careful, he might just fall for this retransmission by the adversary and do something that Alice wasn't intending. So there's, of course, technical solutions for replay, but it sort of mostly goes to show that you really got to be careful in your protocol design here to achieve the sort of all the properties you might worry about. And the paper lays out quite a number of other things you should take into account. So the things I want to sort of maybe highlight here is that there's the paper, one sort of nice thing the paper does is really lays out the main issues that you should worry about when building, sort of constructing or analyzing a messaging system. So one is trust establishment. So this is the question that we just sort of you know, briefly mentioned right now, but we'll spend more time on, is how do these users get the public keys to begin with? The next thing is once you got the public keys, which here we assumed was just by fiat somehow happened, then we got to have a conversation protocol and figure out how we're going to actually exchange messages over the network in a way that's protected. And finally, the question that isn't really as explored in practice in real systems is how do you protect the transport? So suppose that you've already figured out, oh, I want to send the ciphertext C and signature S. I want to get it over to B, but I want to get there in a way so the adversary can't tell maybe that we're talking, or that the adversary can't tell that this is coming from Alice to Bob. And that turns out to be maybe one of the technically quite harder problems to solve in an efficient way. But nonetheless, it's sort of maybe a good way to break up this messaging security world into first getting the keys agreed upon, then figuring out how we're going to protect the message. And then finally, once we encrypted everything, how do you get the encrypted stuff across? So that's the setup that the paper gives us for worrying about these different issues. Make sense? Any other questions about this PGP-like strawman? Sort of works. It's actually not too far from how PGP works in practice. Some people do use this stuff. All right. So the next thing I want to talk about is maybe a different strawman design. So one problem in this PGP strawman is we didn't really have a plan for getting the public keys from user to user, and we didn't really have a plan for dealing with replay attacks that was super convincing. Yeah. You had a question, Raj? Maybe, maybe not. All right. So let's look at a different strawman design to figure out what else we might be able to do. So here's a different strawman that's much more like TLS. So the TLS protocol for talking between servers, you can imagine doing a similar sort of a channel setup protocol between users. So maybe one thing I should say is that TLS seems like perhaps the other building block that you could have imagined, oh, well, like we should just do that and be done with it. Very much like email security seems like, oh, it could have worked, but didn't. TLS also has some good ideas that we're going to try to adopt to the extent it makes sense, but TLS turns out to be not an ideal fit for message security. There's a couple of things going on. One is that in the case of TLS, for server security that we talked about before, you really have a server that you can just go out and talk to. But if you have two users, the buddy that you want to send a message to might not be online right now. They might not have an IP address that you can connect to. This might be sort of not an online protocol that you want to support. You might want to support group communication, in which case TLS doesn't really help you. It's a point-to-point secure channel. You might want to get some properties that we'll talk about later that TLS doesn't provide. So it's interesting to consider this TLS strawman, but turns out that TLS isn't quite the full solution, literally. So the TLS-like plan that you could imagine is that, again, we have our two users, and we'll have very much like TLS, we'll have a key setup phase, and then we'll use that key to later exchange messages. So maybe we'll send a message from Alice to Bob. Alice sends an encrypted message saying, well, encrypt with public key of Bob. Here's some randomness. Let's try to add in that thing we were talking about before. This is Alice talking to Bob. That makes it explicit. And here's some randomness, right? Randomness from A that we're going to use to generate a session key for our actual communication. And then Bob is going to respond back, also saying, well, here's an encryption for you, Alice. This is Bob trying to talk back to you. And here's RB. And now we can compute a key that's going to be the hash of these two randomnesses. And now we can communicate, very much like the picture in the TLS lecture. We can now encrypt our messages with this key K, and we can authenticate it using a MAC, message authentication code. And probably you should use slightly different keys here for the MAC and the encryption by doing two different hashes to generate one key for encryption, one key for MAC. But it's sort of at a sketch level. This is how you might imagine a TLS-based secure messaging protocol. So this works pretty well as well, kind of like the PGP's plan. One benefit is that we avoid the overhead of public key crypto for many of the messages here. We can actually have like a high bandwidth video chat where we send a lot of data here, and we don't have to encrypt it with public key crypto. We can piggyback some kind of a replay avoidance scheme on top of the session establishment. So when we set up a session, we can make sure it's a fresh session by having some kind of a nonce, and then everything encrypted with this key within a session will be easier to maintain freshness of.
I have a question.
Yeah, go ahead.
What's the point of including the Alice's name in this communication? Because can't an adversary just put Alice's name as well in this encrypted message?
Yeah, so that's a good question. So here's the, okay, so let me present two arguments here. One is, I think, what you're roughly thinking, which is that, why don't we just drop this thing? So let me sort of, draw out a version of this protocol where we don't bother including this part. So one line of argument you might have now is that, well, look at this. In order to get this key K, you'd really have to have the one randomness and the other randomness. Now, Alice has her randomness and Bob has his randomness, but to get the other thing requires decrypting either with PKB or with SKB, or decrypting with SKA. So it shouldn't be possible for an adversary to get the randomness. So what's the big deal? What happens if we omit this stuff? So I think here's the attack that protocol designers worry about in this context. And the attack is as follows. Suppose that B wants to do something funny here. So Alice is going to be our victim here. There's going to be another victim on the right. So we'll have another victim C, Charlie, on the right side here. And Bob okay, I'm going to have to change some symbols here in particular. So I think if Alice wants to talk to Bob, we're done, no problem at all. But now if Bob wants to play some funny games here, he's going to interpose on A trying to talk to C instead. So instead of B, let's imagine that this was actually PKC. Alice wants to talk to Charlie. And the message looks exactly the same, especially if we got rid of this source and destination inside the message. Now, when Alice sends this message to Charlie, there's nothing here saying, well, this is intended for Charlie from Alice. It's just some randomness with the public key of Charlie. B intercepts this message and sends it on to Charlie because Bob can't decrypt this. Charlie gets this message as if Bob is really trying to talk to him. Now, this looks like Bob trying to talk to Charlie. Bob just relayed the message. Charlie decrypts this, gets RA, things are good, responds back with an encryption of, under PKB, of some randomness from Charlie. Now, B and C think like they're in a communication, or as far as C is concerned, C is talking to B. But now what B is going to do is it's going to decrypt this because it's encrypted with PKB, and then it's going to re-encrypt it for Alice. So Bob will get RC out and then send it on. Let me draw it sort of here just for space reasons. It'll encrypt this with PKA RC. Now, Bob can't do a whole lot here because Bob doesn't have half of the key. Bob does not have RA. But what Bob has done is he's arranged for Alice to now think, well, let's pretend this middle stuff isn't here. Alice sent this message to C, and Alice got a message as if from C. Now, Alice has key K, which is the hash of RA and RC. Alice can decrypt this thing. On Charlie's side, Charlie also has a key K, which is a hash of RA and RC. They agree on the keys. If they send messages back and forth, they will think, yeah, these messages are making it through, they're correctly authenticated, all this good stuff. But the two sides are confused about who they think they're talking to. A thinks they're talking to C. And C thinks they're talking to B.
Yeah, that makes sense.
Slightly complicated story, but hopefully that made some sense. And maybe the lesson to learn from this is you should really be extremely explicit in all your messages. You should really include information that you expect to be sort of the context for interpreting the message. Like this is intended from A to B. And with that information, right, like if we put this back, C would not have gotten confused. C would have thought, oh, well, B sent me this message, but inside the message it says it's from A. I should send it back to A. Okay, yeah, so hopefully that explains why we want to stick these guys in there. So in this new protocol, I think we talked about this already, but just to like make this point again, it does provide confidentiality, very much like TLS does, except we have a slightly different key setup plan. The one nice thing about this key setup plan is that it's sort of bidirectional and allows us to have sort of flexible plans for how to get the public keys around. And provides some authenticity. If we do the MAC correctly, we'll be able to authenticate messages. We still have to have some kind of a plan for replay attack, but maybe let me not spend too much time on these replay attacks and instead move on to talking about how we're going to get these properties out. So how we're going to get the public keys straight, how we're going to protect the conversation, and then how we're going to get the ciphertexts over the network. Unless you guys have other questions before I erase this stuff about this TLS-like strawman. All right, so let's start talking about trust establishment then. So the problem that we're going to be trying to now talk about is in either of these plans, either the PGP-like strawman that we talked about, where you just encrypt straight up for the recipient's public key, or in this more online protocol that I just erased that looks like TLS, there's a need to make sure that you have the right public key of the other party. And very much like in, as I mentioned before, this is the same problem that TLS struggles with and that it has certificates to help with. So let's talk about trust establishment. So what are the possible schemes? Well, the obvious one that actually turns out to be sometimes used is to just be opportunistic. So the paper cites a particular extension of TCP called TCP crypt that has an opportunistic plan. By opportunistic, I mean you just hope that the other party gave you the right public key. So the opportunistic plan involves Alice talking to Bob and just asking Bob, hey Bob, give me your public key. Bob sends it back over the network. And Alice just assumes everything was good. So TCP crypt does this, maybe more relevantly, SMTP's start TLS, which I mentioned before, also is opportunistic in the trust establishment sense. So when you do this encrypted SMTP over the network, when your mail server connects to a different mail server, these guys don't actually have a plan for how to get the right public key of the recipient. They just assume that the other side gives them the right public key. It's not a horrible plan in the context of start TLS because the whole use of start TLS is opportunistic. You could fall back and say, you know, I can't figure this start TLS thing out. I'll just do plain text. So it's not the end of the world. And this opportunistic trust establishment plan, if you will, I mean, like I guess not much of a plan, but nonetheless, has some actually important properties. So first of all, it is super convenient. So there's no need for users to do any hard work or decisions or key establishment. This stuff just works. And it's not completely useless either. It is actually great at defending against passive attackers. So if your attacker that you worry about is just monitoring the network, then opportunistic security, opportunistic trust establishment is actually a pretty good plan. Because the public key that you will opportunistically get from the other party really is the right key. The bad guy didn't jump in and provide a different key. There was no man-in-the-middle attack. And a particularly important class of passive attackers might be attackers that are just monitoring the network, and then later on, they'll go back and try to decrypt stuff and see what happened in the past. So in that case, if the attacker is just monitoring and wants to then go back in time and like analyze stuff that they recorded yesterday, opportunistic encryption is great. The chance for the attacker to mount a man-in-the-middle attack has passed. So that's pretty cool. So opportunistic trust establishment is a reasonably good idea. But the main downside, of course, where it doesn't work is if you have an active attacker that actually mounts a man-in-the-middle attack. And the man-in-the-middle attack is roughly when Alice wants to talk to Bob, the bad guy jumps in and says, oh yeah, Bob's public key is this other thing that actually happens to be the attacker's public key. And if the attacker does that, then Alice is in trouble. She's going to use the wrong key for Bob that actually happens to give access to the attacker. All right. Any questions about this opportunistic plan? So the other thing that people do, sort of in increasing, level of sophistication of security, if you will, is called trust on first use. Or there's this nice acronym TOFU, which is used in the security community. And the plan here is kind of a variant of opportunistic with key pinning, if you will. So you, as a client, you have an opportunistic trust establishment plan the first time you talk to someone. But then once you've talked to this other person, you remember their key. So it's only opportunistic the first time you're chatting with someone. The second time, you already know them. You have a local file that stores the keys of all the buddies you've already interacted with in the past. This is a pretty widely used plan for something like SSH. So in SSH has a file called known_hosts on your computer that saves all the keys of computers you already connected to. The first time you connect, I guess strictly speaking, it asks you, here's a fingerprint, do you trust it? But most users just say yes, and it saves the key in this file. But then on later uses, you already have the key, so you don't have a trust establishment problem. So again, the nice thing about trust on first use, it's convenient, very much like opportunistic is convenient for establishing new trust and maintaining it as long as things are working out okay. It's actually good against a stronger attacker than just opportunistic. So in particular, if you have a new active attacker, then tofu is pretty good. So if you talked to your buddy yesterday and got the key, and today there's some bad guy out to get you, they're not going to be able to mount a man-in-the-middle attack because you already have the right key of your buddy. The one downside, well, there's, I guess, two main downsides of tofu. One is that it doesn't really work against the determined attacker. If the attacker has been there all along and man-in-the-middle the first time you try to talk to your buddy, then you're in trouble. This is not going to save you. And the more annoying thing, if you will, in the common steady case, if you will, is rekeying. So the scenario to have in your head is that I talk to my buddy Bob, and I have his public key. But for some reason, Bob broke his cell phone and got a new cell phone. And that new cell phone has a new key. And now I have a key for Bob. I know that's right because of my tofu plan, but Bob's device has a different key. And now I have a message that says, well, you're talking to Bob, but Bob doesn't seem to have the right key. Someone's impersonating Bob. Now, in practice, probably what happened is that indeed Bob had to reinstall this application or get a new device. But the downside is that this gives an opportunity for the attacker to pretend like Bob has a new phone, and Alice might fall for this. Alice might then accept the new key as if it was really Bob's key. Make sense? Questions about this tofu plan? All right. So the other thing that some systems do is rely on some kind of an out-of-band exchange. So the idea is that no matter what we send over the network, we're going to be able to have a strong basis of trust in the other party's identity. So instead, what we're going to do is require users to give themselves, exchange public keys on business cards, or a common plan, for example, is QR codes on your screen. So if I want to talk to Bob, we get together in the same room. I push a button on my chat app and it shows a QR code. Bob scans this in, and that gives Bob my public key. And I do the same for Bob. And now our cell phones have exchanged public keys by scanning each other's QR codes that encode the public key of that party. So this out-of-band exchange plan is actually really good in terms of security. So it's basically as good as you could hope for, because we literally walked up to each other in some way that we think is secure and exchanged our public keys. And from that point on, these cryptographic protocols are going to work great. The downside, of course, is that it's actually quite tedious. So these days, I'm stuck at home. I can't really go anywhere outside. So how am I going to exchange QR codes with my buddy? Even if they're not that far away, maybe I can't go outside and see them in person. How are we going to establish a secure messaging channel here? And the other problem is that actually, even with this manual key exchange plan, this rekey problem is still there. So even if I met my buddy before this quarantine lockdown, we exchanged keys through out-of-band, everything was great. And while my buddy has been locked up at home, he broke his cell phone and got a new one, or switched applications or reinstalled it. Now I'm back to where I started. I don't know what my buddy's key is anymore, even though we had this great plan beforehand. So these sort of schemes, as you can see, they're sort of trying to be more secure, but there's some common themes that we keep seeing here. So maybe it's worthwhile to highlight them, because I think the takeaway is really sort of these themes that you got to worry about, and not so much the exact schemes. So one theme we are seeing over and over again is this convenience. So convenience really ends up trumping quite a bit of stuff. Users have to be on board with using your system, and if your system is too hard to use, they'll just use something else and not be secure. So in that sense, you could almost think of usability and convenience as a security requirement in order to actually really protect real users' conversations. Another theme that we see coming up over and over is this rekeying. So like rekey is the same thing as recovery. So dealing with lost devices or reinstalled or regenerated keys, turns out to be a big deal, and doing it securely is important. And the right mindset to have for worrying about rekeys is really, how is the attacker going to be able to abuse this mechanism? So you have to support rekeying of some sort, because users will change keys because they lose their devices, etc. And whatever workflow you have for introducing new keys back into a system for an existing user, the bad guy could try to take advantage of it. And if that turns out to be the weakest sort of step in your protocol, the bad guy will just inject their key through this recovery plan. Another thing to sort of maybe note here is that almost all systems are going to have combinations of these schemes. You might have out-of-band exchange, maybe with a fallback to tofu, with a fallback to opportunistic, depending on what the users are, sort of how the users found each other and why they trust. So this usability is really a system-wide property. So it's not really a matter of, well, this cryptographic technique provides good usability, but really usability is really a question of how do you put these cryptographic and system design techniques together to make sure that the whole application provides the right sort of abstractions for users to do this right. Make sense? Questions about this stuff so far? So the next thing I want to talk about is a pretty widely used plan for trust establishment. These guys are all peer-to-peer, if you will, that don't involve any kind of a server. But it turns out it actually is extremely helpful to have some kind of a server in charge of distributing public keys. Very much like we had a certificate authority in the context of websites with HTTPS last week. Many messaging systems rely on a key server to distribute public keys to users. So for example, Apple's iMessage works like this, where there is a server out there that has everyone's username and public key. And if Alice is a user in the system, then PKA appears in this table. And Apple, in the case of iMessage, takes responsibility for running this server and basically doing two things. One is allowing anyone to query this table. That turns out to be non-trivial because you want to avoid spam and monitoring of users and all this stuff. But nonetheless, Apple allows users to query this table to find public keys of different buddies. And also, Apple is going to sort of be in charge of authenticating insertions into this table. So Apple claims they know all these users in the sense that they probably didn't have a password or other ways of authenticating these users. And a user, if they authenticate to Apple, they're going to be able to change their public key in order, or insert it in the first place, and then afterwards change it if they want to actually change their key. It's very much like a CA scheme for messaging system. So one nice property, well, like I guess several nice properties about this. One is super convenient. The user doesn't have to do a whole lot with this system. It's almost like opportunistic security, except that you magically get the right key if you trust Apple. Another nice property is that very much like in the CA world, if the Apple server here, this authority, is honest, they cannot snoop. So what I mean by this is that if Apple gives out everyone the correct public key, then the whole system will be secure, and Apple, even if they want to try to snoop as to what's going on, they cannot. The messages that they see are all going to be encrypted with the right user's public key. And the last sort of really cool property of this plan is that finally we have a good answer for rekeying. All these previous plans, we didn't really know what to do with giving a new key for a user, but in this plan, there's actually an answer. So if Alice wants to use a new key, Alice just logs into her iMessage account at Apple, and her device is going to upload a new key and stick it in this table. And all of Alice's buddies are just going to get the new key by querying the iMessage server. And this will work out pretty well. The downsides of this plan, of course, are sort of twofold. One is that, as we've seen, we have this guarantee about an honest Apple server not being able to snoop, but a malicious Apple server can man in the middle. because this guy is trusted. If someone compromises Apple's iMessage key server, this is really bad news for Apple because, or Apple users at least, because this compromised server can give out the wrong public key, and we're back to basically opportunistic encryption, or maybe even worse. And the other problem is actually rekeying is an attack vector. What I mean by this is that previously in something like Tofu, once I got a user's like the public key of one of my buddies, I was in pretty good shape. But in Apple's scheme, if someone steals the password of my buddy's iMessage account, that bad guy can change the public key in this table, and my device will all of a sudden start using this bad guy's public key. So by allowing an easy rekeying plan, the credentials needed for that rekeying become as valuable as the public key itself almost, because you can change the public key if you can log into the guy's iMessage account to change entries in this table. So we see this tension with recovery, right? Like if we make a clear and convenient plan for recovery in this example, we've introduced a weakness that an adversary can take advantage to force recovery or force rekeying. That make sense? So the central key server design is pretty widely used. I think a bunch of messaging systems in practice use it for many of these reasons. It provides sort of convenience. You often need a server to support asynchronous messaging. It's pretty good if the server is honest, allows some kind of a rekeying plan. But this is a real issue. The sort of amount of trust that you place in the server has made quite a bit of system designers a little bit uneasy. And what I want to talk about next are basically two extensions to this key server design that try to mitigate some of these problems to some extent at least. Not fully solve them, but try to make some progress at least on those directions. All right, any questions so far before I jump into these refinements of the key server plan? All right, so the first extension of this key server design is called key transparency. It's a fairly active ongoing project by Google and others trying to basically audit the behavior of these key servers. So the idea is that we have this key server, which we were looking at before, which has this table of a username and the public key of that user. So we might have our Alice here with PK of A. And the design for this idea, key transparency, is to introduce a log, an audit log of some sort, that will contain all the operations that the key server does. So for example, when Alice first registers, the audit log will say Alice added PKA. That's a log entry. And then when Bob registers, maybe it'll say, well, Bob added PKB. And then if Alice wants to add another key, it'll say, well, Alice added another one, PKA2, and so on. So how does this help? It seems like a little bit of a, just rephrasing this table in terms of a log. So what's going to happen, let me first describe how users are going to interact with this scheme, and then we'll try to see how this is going to provide security. The intuition is going to be that we're going to try to force this log to be append-only and globally consistent. We'll look at the techniques actually in later lectures, but the basic idea is that when Alice wants to send a message to Bob, she will do a lookup in the server and say, well, I want to look up Bob. And the server might say, well, the response is Bob has this public key from the table over here, let's say PKB. And by the way, here's proof from the log. And the proof is somehow going to prove that the last entry for Bob in the log really is PKB. And that's true right now, in this at least design on the board that we've, in this example on the board. So now Alice is convinced of actually two things. One is that the key server thinks this is Bob's public key. And second, the key server logged this public key into this audit log. And this is going to help because periodically every user, including Bob, is going to look up their own public key from the log. And Bob is going to get an answer back saying, well, here's the proof. The latest entry in the log for you is PKB. And perhaps he can get a log of all the previous entries and so on, anything related to Bob. Now, the cool thing is that if we can somehow figure out how to make this log append only, so that the key server, even if the key server is malicious, they have to maintain this log in this append only style, only keep adding to it, they can't delete old entries, then we're in pretty good shape, because if the key server ever lied to Alice about Bob's public key, the key server would have to stick the lie into the log in order to provide proof to Alice. But if the key server lied and the log now says Bob added PKX, then Bob will eventually notice this. When tomorrow Bob queries the log for its own records, it'll say, oh, like someone added PKX for me. What the hell is going on here? Bob knows that's not right. And then Bob might do something like inform all their buddies that I've been compromised, or the key server is out to get me, etc. So I think that's the cool property about this log key transparency plan, is that it allows us to not prevent malicious servers, but at least catch them if the server lies. And of course, this is a bit of a magical data structure I've described so far. There's a lot of technical challenges here. And roughly speaking, you have to have efficient lookups. So this lookup and proof from the log have to be fairly small. You can't just ship the whole log back and say, oh, look, here's like the terabyte of key operations that have happened. Good luck. So we need some clever data structure that makes it easy to generate these efficient proofs. We have to somehow make sure that this whole log is append only, that the server cannot cheat, and there has to maintain a single log. And there's a bit of a concern also with privacy, depending on your use case, that maybe you don't want this to be a list of all the users in the universe and what they're doing. So this is gonna look probably closer to, well, some of the techniques we're gonna talk about next week in the Sunder paper are gonna start to answer what this design might look like in a cryptographic design sense. But there's if you Google for key transparency, you'll see there's a nice GitHub repo with a prototype of this design worked out, and it describes how they actually achieve these techniques in a bit more detail. All right, so that's the first sort of sophisticated key server extension that I wanted to mention. Any questions about this extension before we move on to next things? All right, so the other sort of cool idea, maybe the last thing I'll mention in this trust establishment sense, is a better way to find your buddy's public key. So this is a system that we actually have a guest speaker in a couple of weeks from the founder of this company, Keybase. And the sort of core technical idea that Keybase is trying to provide is basically a more like a key server with a better way for users to make sure they're talking to the right buddies. So the idea here in Keybase is that they'll still have a key server whose job will be to maintain user to public key mapping. So we have Alice here and Bob, and also there's PK of Alice, PK of Bob. But in addition to just this table, the server is going to maintain other identities for these users. So for example, for Bob, this identity table might say, well, this guy who's Bob at Keybase has actually a Twitter account. And this Twitter account is, I don't know, let's call him MIT Bob. That's his Twitter account. And the idea here is that in order for me to gain confidence that I'm talking to the right Bob, I might already have a good idea of what their Twitter account is, or GitHub account, or Facebook account, all this stuff. And what Keybase is going to do is it's going to ask this Bob user to stick some kind of a signature into their Twitter feed, proving that their Twitter account belongs to the same person as their Keybase account. So in particular, what's going to happen is that on Twitter servers, separate from Keybase, no affiliation at all, in MIT Bob's Twitter feed, that user is going to post a message signed with their secret key saying that, yeah, the guy who is like Bob on Keybase is MIT Bob on Twitter. And what this allows us to do is when a user like Alice wants to find Bob's public key, they can look up Bob here in Keybase, and the response they're going to get back is the public key of Bob, as well as other identities that should convince Alice this is the right Bob. So it might actually say, well, go look at MIT Bob on Twitter. And then Alice can actually go to Twitter and query the list of tweets or messages that MIT Bob posted. Maybe she has a hint as like, well, it should have been like, I don't know, last month. And then the response is going to be this signature by, SK of Bob, that's the right Bob. And now the question that Alice really has to answer is she trying to talk to the same Bob that's MIT Bob on Twitter, and it's like, I don't know, Bob MIT5 on GitHub. And this list might have multiple identities. And now Alice really has to, like the client that Alice is running has to pose this question, like, did you mean MIT Bob on Twitter? And if that's the case, and MIT Bob's Twitter account hasn't been compromised, now Alice has a pretty good idea that, yeah, she got the right public key. Because MIT Bob would only post things signed with his real public key on his Twitter account, and Keybase gave Alice the pointer to go check that out. Hopefully that makes some sense. So the cool problem that this is solving is that we don't have to fully trust this Keybase server. Even if the Keybase server is compromised, it will not be able to supply the wrong public key to the client as long as the client goes and checks out these references for other identities of the buddy they're trying to look up. Any questions about this Keybase plan and what it's providing? So as I mentioned, right, like this is just sort of one slice of Keybase. The particularly cool thing they're doing here is sort of linking other identities to your Keybase identity. Seems like a really powerful idea that you should know and maybe use even in another context, not just as a Keybase user. That seems like a cool trick. Keybase, the system, of course, has lots of other ideas. It has a thing kind of similar like to key transparency. It has a rekeying plan that's much more sophisticated and so on. But maybe I'll let Max Krohn describe this in more detail in his guest lecture in 2 weeks or so. All right. So if there's no questions about Keybase, this is probably the most sophisticated trust establishment scheme that I know of or I'm going to describe in this lecture. So I'll move on. Well, feel free to ask a question, but my plan was to move on to now conversation security. This is the problem of once you've gotten your buddy's correct public key, how are we going to actually encrypt messages and make sure that the bad guy can do something undesirable to our messages over the network? All right, so conversation security. So this is, I think, unlike trust establishment, where there's a lot of sort of annoying details, if you will, or hard to solve technically problems like trust establishment, where there isn't really a technical solution in many senses. You have to sort of play with what do users already know, what are they going to be able to use in practice, like this Keybase idea. There's some clever crypto in there, but it's more of an observation. Like, here's a good way to bootstrap trust, almost independent of a cryptographic protocol. In contrast to that, conversation security is much more sort of full of technical ideas that just work. Because the nice thing is for conversation security, the starting point is we already have the other guy's public key or whatever other notion of trust establishment that we need. And here, it's much more of here's a almost cryptographic or system design puzzle. You could just solve it. If you solved it, you're done. In some ways, satisfying in a way. And there's a lot of desirable properties. What makes it hard is that there's a lot of things you might actually want out of a messaging security scheme. One particular thing that you might take away from the paper is that, boy, groups are hard. So if you have conversation between multiple users, there's just a lot of properties you might care about consistency, about privacy, all this stuff. And this is a really challenging thing that has some, non-trivial trade-offs in terms of designs that people have come up with so far. And many of the group chat designs are actually not that great. So for example, the Zoom system we're using now, the group security plan here is that there's a server at Zoom that gives all of us a secret key. And then we just run with it. And we just encrypt messages to each other. But there's nothing really much stronger in Zoom than that. And it's not maybe the greatest plan. The paper talks about many other schemes that you could do better. Another thing that makes conversation security hard is there's a lot of actually seeming tensions between requirements. So one that I want to talk about in maybe a little bit more detail is the tension between authenticity and deniability. So on one hand, we want authenticity. That was like one of the, our number 2 goal early in this lecture was that we want to make sure that when we get a message, we're sure who it came from. But another property that you might want out of a system is deniability, meaning that it's kind of like a conversation with your buddy that no one is recording. Even though you're talking on a computer, it shouldn't be possible for someone to produce a cryptographic proof that, oh yeah, Nikolai said this, and then his buddy said that, and well, they shouldn't have said that. So it would be nice if we had a cryptographic or a conversation security scheme that provided us deniability, but can we get authenticity at the same time? So this turns out to be like a surprising, cool technical result that shows that, yeah, you can actually get both. You can get authenticity, like I'm convinced that my buddy is chatting to me and he's convinced I'm sending him messages, but no one can produce a proof that this happened. Another actually more recent tension that came about is confidentiality, which of course seems like a good idea, versus spam or harassment. So what I mean by this is that you want your messages to be encrypted so that they're confidential, but if no one can look at the contents of your messages, you might be able to send lots of spam or lots of harassing messages to lots of users in a system, and those users can't report you, the system can't filter them out because they can't look at the contents of the spam. You can't, like the recipient of the message can't prove that this message was sent perhaps. Kind of an annoying situation. And there's also some cool technical solutions to this problem as well that probably we won't talk about in this lecture. So maybe let me start off by talking about this actually cool technical trick of how to get deniability while providing authenticity. So the context, just to sort of recap the same diagram we've been drawing over and over, is that we have a user A who wants to send a message to user B. And the goal is that we'd like for B to be sure that the message came from A. Otherwise, the system isn't providing a whole lot of guarantees here in terms of knowing what's going on. But we'd like to be sure that B cannot prove to others that A sent this message in. It's like a private conversation. I have a conversation with you. We're pretty sure we're talking to each other, but my buddy can't run off and like later go to the newspaper and say, oh, well, I have proof. Nikolai said this. Well, maybe I shouldn't have said something. Even more strongly, we'd like to say that B cannot prove that A even talked at all. So even a stronger property is that B can't even convince anyone that I talked to B in the first place. Pretty strong requirement. Now, you should really interpret these requirements in the context of the sort of cryptographic technical protocol design. there might be other kinds of proofs other than cryptographic proofs that B could produce. Like maybe our ISP has been monitoring our messages, and the ISP has a record, like Nikolai sent this IP packet to his buddy. And if you trust the ISP, you might take the ISP's proof, because the ISP might say, well, yeah, well, I looked at my logs, Nikolai sent this packet to this buddy on this port, on this date and time, they talked. So that's sort of the kind of proof that at least this protocol isn't going to address. This is more of a question for the transport privacy problem that the paper laid out. We're probably not going to have time to talk about that. But here we're going to try to figure out how do we avoid cryptographic proof of this happening. And just to remind you, the two strawman schemes that we put up early in this lecture don't really meet this requirement. So for example, in the PGP plan, when Alice sends a message to Bob, Alice sends a message and a cryptographic signature using her private key. That cryptographic signature is pretty damning evidence that she really did send this. Bob can just take this signature and show it to the newspaper or to anyone else that asks and say, oh, like, I got a signature from Alice. She sent this. No one else could have made that signature. So somewhat surprisingly, it's also true that the TLS-like strawman is also not deniable. And it's not deniable in the second sense, because in the TLS strawman, what we had was signed messages. We might have, there's some, the particular strawman, we like, if you use TLS to actually establish connections, then the TLS protocol involves users using their keys to sign messages. And in that case, Alice must sign a message in that protocol to demonstrate that it's her talking to Bob, to convince Bob. And then, even though she's maybe not signing the subsequent messages, she's going to sign some key exchange message, depending on the scheme we're talking about. And that is going to give Bob the evidence that at least Alice tried to talk to Bob. That might also be an undesirable thing for us to try to avoid. So here's the clever trick that I want to describe. And the idea is basically never sign anything, no signing. And instead of signing, use these message authentication codes, which is kind of like the symmetric key analog of signatures. But crucially, there's no private public key pair duality. There's just a single key that is used to compute a MAC. It's like a keyed hash or a checksum. So here's the scheme for doing deniable messaging. So if A wants to send a message to B, what's going to happen is that first, this is like what we'd like to achieve. What's actually going to happen in the protocol is that B is first going to send an encrypted key to A. So it's going to take public key of A and send some randomly generated key to Alice. And now what Alice is going to do is send her message. I suppose we should encrypt it, because why not? And for privacy at least. Here's a message encrypted with the public key of Bob. And by the way, here's a MAC. So a MAC using this shared key that Bob sent over that message M. So after this exchange, I want to argue two things. First, we have authenticity. So Bob looks at this message. Bob can decrypt this message. Bob's got the corresponding secret key. And Bob can check this MAC. And from Bob's point of view, no one should know this random key other than Alice, because Bob sent this key to Alice. So if Bob sees the correct MAC computation here, it must have been Alice. No one else has the key. So Bob is convinced this was Alice sending the message. Here's the really cool thing. Suppose Bob wants to go to the newspaper and say, oh, look, Alice sent me this message. Bob can produce all the network messages that were ever sent. This message, this message, this message. And here's the cool thing. Anyone else that wants to, so to say, frame Alice for sending a different message M can do so. So if I want to cook up some other message X, well, suppose I want to frame Alice for sending message X. What I will do is I will cook up my message X. I will encrypt it for Bob, PKBX. Now I need to cook up a legit looking MAC. What I'll do is I'll cook up a new key, K prime, and I'll MAC my fake message with this fake key. These look like these messages in that protocol. And now I'll go back in time, logically speaking, and take my message K prime and encrypt it for PKA. So I can, or anyone in the world, can frame Alice for sending any message of their choice. Any message X, they can cook up any key they want, and this set of messages looks exactly like the legit set of messages. So this is what makes the protocol deniable. Anyone can produce a trace of network messages for any message, which means that any particular trace of messages that Bob might be claiming doesn't look any more legit than any other fake set of messages. Sounds like a really cute technical idea. Any questions about this construction? Or deniability in general?
But so this doesn't allow, this still allows Bob to claim that Alice did talk at all, but not
here's the thing, no,
specific
because
content.
I could claim this about any user in the world. I could claim this about you. I could take your public key and stick it here, and it will look like as if you sent this message X to me. I don't even have to have, this doesn't even have to be me. I can take any pair of users, like, I don't know, the 2 TAs in this class. I'll stick, that was one TA's key, this is a different TA's key. I'll make up a message I want to make it look like the 2 TAs sent to each other. I'll cook up this transcript for any pair of users.
But you could say though that he did initially send this key to Alice, though.
Well, I could
using
say it, but
Alice's
it's not going to be
public key.
convincing. And the reason it's not going to be convincing is that anyone in the world can make an equally legit looking trace of red messages that I have drawn on the board here. They're going to be indistinguishable from what really happened. So that's the reason why it's deniable, is because a fake set of messages looks indistinguishable from the real set of messages. There's nothing that makes this thing very checkably fake. All right. If you want, we can chat a little bit more afterwards as well. So I wanted to wrap up. So we talked a lot about trust establishment in message security, a little bit about conversation security. There's some stuff in the paper about transport privacy that's kind of cool. It's like a stronger version of this deniability story that works even against ISPs. But maybe the sort of high-level point is that there's really a pretty active area of research and development and sort of real systems getting deployed. And unlike TLS, I think this is much less of a done deal. There's many more things to explore and to figure out that haven't been solved yet. And it seems unlikely that there will probably even be a single solution, partly because there's so many trade-offs to be made in the trust establishment part of this problem. All right, so that's it for message security for this lecture. We'll talk to you guys next Wednesday about how to do secure untrusted storage systems. That's going to be the Sunder paper. That's going to be quite a bit of similarity to Lab 5 that you're doing at the end of the class. All right, thanks very much. See you guys on next Wednesday.